Okay, so what do I want to do today? I want to do a few things. The first thing I would like to do is cover a couple of things that I didn't quite get time to finish last class about thermodynamics. So just a couple of concepts, sort of around thermodynamics I'd like to talk about. And then I would like to actually talk about the quiz that's next week. So, and I would actually like to go through a full practice quiz. And then once we're done with that, I will look at some of the new content that comes after thermodynamics. Now, the thing I want to say is that we're actually very close to the end as far as material is concerned. So keep in mind that you have 2 DLs this week and then 1 DL next week. Some of you might have a slightly different schedule than that, but there's 3 DLs left in the curriculum. DLs 15, 16, and 17. And so we're basically done with new material. And so I don't really need 2 full weeks of lecture time to fit in the rest of the material. So we'll do some of it today and we'll do some of it next week. And we'll also talk about a bunch of other things next week. So that's what I'll use that time for. But the point is, once I'm done with going over that one practice quiz, I will go ahead and introduce some of that new material, but not all of it. We'll sort of save some of it so we have something to do next week. Okay. So like I said, if you have any questions, please do not hesitate to ask them. Either in chat, you can message them to me directly if you prefer, or you can post them publicly in chat, or you can raise your hand and speak out loud. It does not matter to me which one you choose, whichever one makes you most comfortable. Okay, so this is the slide that I have, the title slide for this particular topic. And it says flipping coins for some reason. And the reason I say that is that we are going to be thinking about flipping coins today, which is going to feel really slightly absurd. Like, we're doing physics. Why are we now flipping coins? It doesn't make a ton of sense. We'll see why. We'll get there, but we're not going to worry about that right at the beginning. Instead, we're just going to do some review on the thermodynamic stuff and talk about a couple of little thermodynamics topics that we missed. So what is thermodynamics? Thermodynamics, we said, is an extremely general model, but for our purposes, it's a model that specifically applies to gases. And what's special about gases is that gases can change their pressure, volume, and temperature as energy is added or removed. And what makes things interesting is that when gases change, the change in pressure and volume and temperature actually also affects the internal energy. So if I add energy to a gas, its internal energy is going to change. And it's then going to change its pressure and volume, which will also affect the change in internal energy. And so we have to take these changes into account when we're working with gases. Now, other types of substances do this as well. So solids and liquids, for example, also have pressure, also have volume. The pressure of a solid is a little bit of a poorly defined thing, but we're not going to worry about it. But liquids certainly have pressure. Everything certainly has volumes, and those things do actually change when temperature changes or when the internal energy of our system changes, but they don't change by much. And so we don't usually have to think about them. But for gases, the change can be quite dramatic, and so we do have to think about it. And the thing that we use for this is the ideal gas law. The way that we can think about the ideal gas law conceptually is it just says that the temperature of the system affects the pressure and volume. The temperature of the system affects the pressure and volume. Well, there are actually a couple ways to think about this now, right? The temperature of the system affects the pressure and volume. You could say the pressure and volume of the system affects the temperature. Another thing that you could say, though, if you wanted, was that the pressure and volume are proportional to the thermal energy of the gas. What do I mean by that? Well, on the right-hand side of the equation, we have the number of moles times R, the ideal gas constant R times the temperature. That number is not exactly equal to the thermal energy of a gas, but it's related to the thermal energy of the gas. There are just a couple of things we'd have to multiply it by to get there. And so another way of thinking about this is that the pressure and volume are similar to, but not exactly equal to, the thermal energy of a gas. And of course, in gases, right, we don't have bond energy. And so the only kind of internal energy that gases have is thermal energy. Right? A gas has zero bond energy. That's sort of one of the definitions of a gas. And so we only have to consider thermal energy when thinking about changes in energy inside of a gas. And then what we said is that at its core, thermodynamics is still about energy conservation. So this is a new form of an old equation. And it just says that the change in the internal energy of the system is equal to the heat plus the work. That's all that it says. This is an equation we've seen before in different forms with different variables, but it means the same thing. The change in the internal energy of the system is equal to the heat plus the work. Heat is still just energy moving from one place to another. It's the same kind of heat that we've talked about. But the work is a little bit different, right? It involves the pressure and the volume of the gas. And we saw this fancy integral formula that we're not going to use. But in simpler cases where the pressure is constant, we can calculate it using this equation. Work is equal to the negative pressure times the change in volume. And there are also cases where pressure is not constant, but we can still calculate work. And we'll see one of those examples here in a little bit. And then we introduced this idea of what's called a state function. And a state function is something that we can measure about a gas at a particular moment in time. So for example, I could take the gas at a particular moment in time. I could measure the temperature and say, what is the temperature of this gas at this moment in time? That is a meaningful question to ask. That's a question that we can answer. We can do that. I could ask, what's the volume of this gas at a particular moment in time? What's the thermal energy of this gas at a particular moment in time? These are all questions that presumably have an answer. Whether or not we exactly know how to get to them is not necessarily for sure. But they're certainly questions that make sense. They're questions that we could answer given enough time and enough, measurements and stuff like that. What we could not ask is, what is the work of this gas? How much work does this gas have at a particular moment in time? That doesn't make sense, right? Because work is something that happens over a period of time, right? As the gas expands, work is done. But it's never something that you can measure about the gas at a particular moment in time. And often we like to represent information about state functions on these things called state diagrams. And what's nice is that the state diagram actually packs more information into it than we actually might notice at the beginning. So for example, one of the most common types is a pressure volume diagram. Now, what can we get off a pressure volume diagram? Well, obviously we can get pressure and volume because that's what the diagram is about, is pressure and volume. But we can also get other things. For example, we could get the amount of work that's done. Right? The amount of work that's done is going to be equal to the area under the process. So for example, let's say, whoops, that's not what I meant to do. You have this process here, and we're perhaps interested in the area, in the work done during this process, right? Now, we couldn't calculate this directly, but if we could calculate the area under this line, that would give us the work that's done during this process. But also, the pressure volume diagram has other interesting information on it, such as information that could be used to find the temperature of the gas. So if we go back here, we know that pressure and volume are related to the temperature of the gas. And so if I can get the pressure and volume off the pressure volume diagram, I could, in principle, get the temperature. So there are all these nice things. Whoops. My bad. Let me reshare that. There are all these nice and interesting things that we can get off of pressure volume diagrams that are somewhat useful. And then the last thing we learned was about these 4 kinds of special thermodynamic processes. I'm not going to talk about them a ton. Again, you don't need to know off the top of your head what the words mean. So for example, if I told you that you have an isochoric process on a quiz, I would then say, oh, and this is a process where volume does not change, or volume does not change. An isobaric process is a process where pressure does not change. An isothermal process is a process where temperature does not change. And an adiabatic process is a process where no heat is allowed to enter or leave the system. These are types of special thermodynamic processes. They show up all sorts of places. So for example, an adiabatic process, which is kind of the weirdest one, at least mathematically, which is why we're not going to think about it a ton, mathematically at least. Adiabatic processes are often used, or we can often think of certain processes in car engines as adiabatic processes, right? So it's a process where something's expanding and that expansion is causing it to do work, which, for example, is being then used to turn the wheels in your car, but there's no heat entering or leaving the system during the process. That's what we call an adiabatic expansion. So what are the new topics or the new pieces of thermodynamics that I want to cover before we go to the practice quiz? And I want to think about states and processes again, and what makes a state so special. So what do we have in front of us here? Well, we have a pressure volume diagram, right? It doesn't have any numbers on it, but we don't need them for this. And we have state 1 and state 2, and there's 2 different ways we can get from state 1 to state 2. The first is to go like this. We go over to the right and then up. And then the second one is like this. We go up and then over to the right. Okay. Those are 2 different processes, but they start at the same state and they end at the same state. So what's special about this, right? So in this case, you could imagine in this direction. So let's take this process first. This is an increase in pressure with no change in volume, followed by an increase in volume with no change in pressure. So what you can imagine this as is like you have the balloon that's heating up for some reason, but it's being held in place, so it can't expand. So it's just getting warmer and its pressure is going up, and then it expands, right? And then this other process is the exact opposite. First, it expands, and then it just sits there while its pressure increases. And what's special about these is they start at the same state, which means the pressure and volume have to be the same here, right? For no matter if you're planning on going this way, you're planning on going this way, it doesn't matter. Pressure and volume here are some numbers, and they're the same for either process. And because of the way that state functions work, the pressure and volume at state 2 must also be the same, no matter whether you took this direction or you went this direction. But there's more than that. It's not just the pressure and volume that will end up being the same at the state 2. It's also all of the state functions that will be the same, even the ones that are not on the diagram. So the temperature will be the same at state 2. The thermal energy, the internal energy will all be the same at state 2, no matter how you got there. That is the beautiful thing about state functions. But, what will be different? Well, the difference will be, for example, let's say we wanted to know the amount of work that's done during one of these processes. Those numbers are not going to be the same. This direction, you're going to have different amount of work done than if you go this direction. There's going to be different amounts of heat, for example, as you go, if you go this direction than if you go the other direction. So that's one of the things why we call process functions and state functions, right? State functions only depend on the exact spot you ended up in. They do not care about anything else. Whereas process functions do actually care about how you got there. So let's use that information on this example. This might look like the same example, but it's not quite the same example. In this case, we're starting down here at state 1, then we're going to the right, then up, then left, and then down. And so we're starting and ending at the same place, right? We're starting at the same pressure and volume as we're ending at. Now, what's special about these kinds of processes? Well, let's think back to what we said earlier. Let's think about a state function that's not on this diagram, like the internal energy of the gas. And let's imagine starting at state 1 and going all the way around and ending back at state 1. What do I know about the total internal energy of the thermal energy, of the gas when we get back to state 1? Well, we know it has to be the same as when we started. How do we know that? Well, what I've said is that no matter how you get to a state, the value of all the state functions will always be the same there. And so at this state, it doesn't matter if we started here and went all the way around and then came back, or we started here and went way over here somewhere and then came back, or we started over here and then, went up this way and then came up and around and then back down and then came back. When we get back to state 1, all of the state functions must be exactly the same as they were the last time we were at state 1. So pressure will have some number. It'll be the same when we get back to state 1. Volume will have some number. It'll be the same when we get back to state 1. Temperature will have some number. It'll be the same when we get back to state 1. And the other nice simplification with cycles is that the work is now just equal to the area inside the shape. So no matter how weird the shape is, the work done during the process will always be the area inside the shape. Okay, so we're going to use this information here in this practice problem I'm about to do. But what are the kinds of problems that we can see for the model of thermodynamics? Well, there's a few things. Thermodynamics involve several, usually they involve these pieces. The interesting thing about the model of thermodynamics is that the number of problems that we can write is fairly small. There's not a ton of different things that we can do. And for that reason, there's a lot of practice quizzes. The practice quizzes have already been posted. I think there are 10 of them that I am sort of okay with and have solutions for. I'll talk about why I picked the 10 I did here in a minute. But usually what happens is this. You have a pressure volume diagram. And there's going to involve these several things: changes in temperature, changes in pressure and volume, work, and heat. Right. So, and usually what will happen is you'll be given enough information to calculate one or two of these things, and then you have to use what you find to then calculate something else. That's usually what it's going to look like. Like I said, we'll look at a example here in just a minute. So let's actually do that right now. Pardon me. Yeah, so even though my symptoms are pretty mild, 0 of 10 don't recommend still that. Okay. Okay. So let us take a look at this. So this is one of the practice problems. Like I've said, they've already been posted. Hold on, let me get this working. They've already been posted, so you can go check them out. The solutions will be posted here in a minute, or in a couple of days, as usual. But this is one of them. This is one of them. Now, one thing that it does not include is the particle model of thermal energy, which may be included on your quiz, but there are some practice quizzes that do. But I want us to look at this practice quiz and think about it for a few minutes and see how we would go about solving it. So let's read it real quick. So it says, depicted on the right is a thermodynamic cycle performed on an ideal gas, which means there's no phase change. Process A to C is an isothermal process, constant temperature. Process B to C is an isobaric process, constant pressure. And process C to A is an adiabatic process, Q is equal to 0. Note that you are given pressures at state A and C and volumes at states B and C. Okay. What is delta U for an entire cycle? Now, at this moment, this is an example of where it would really cause problems to go straight to the equations, because your first instinct might be to, oh, let me see if I can go find an equation that would solve this problem for me. But that would actually not get you any closer. In fact, it would probably be more confusing. So let's think about this purely from a concept perspective. What is delta U for an entire cycle? So what do we mean by an entire cycle? What we mean is that we start at state A, right? We start up here. We go down, or excuse me, no, we go not that way. We go this way. We go down through this process to B, from B to C, and then C back to A. I'm just getting some pretty, I'm getting a runny nose here for a second. Okay. So what is delta U for the entire cycle? So again, let's think back to what we just said about cycles, right? Cycles start and end at the same state. So what does that mean? It means that the value of all of the state functions will be the same at the end as it was at the beginning, right? We're starting at A. We're going around, well, it's not a circle, but it's a cycle, right? It starts and ends back. It ends right back where it started. And so the value of all the state functions will be the same at the end of a cycle as it was at the beginning of the cycle. So what does that mean? It means this. Right? U is a state function. Right? It starts and ends. It starts and ends at the same state. Ends at the same state. right? The system starts and ends at the same state. That means the values of all the state functions will be the same at the start and end. And that means the value of internal energy will be the same at the start as it is at the end. And that means the total change is 0. So again, no calculation needs to be done here. We don't need to do any calculation. We just need to apply something that we know about cycles in thermodynamic processes. Okay. Part 2, determine the sign of the work done by the entire cycle and the sign of the heat transfer for the whole cycle. Explain your answer. So this is again something where we might be tempted to go to an equation sheet, but we don't need equations here. We don't need equations here. I'm going to show us why. Now, one thing I briefly said is that when you have a cycle, work is going to be equal to the area done, the area inside of the shape. And that's true. We cannot calculate the area inside of the shape. It's not a nice geometric shape. It's got these curving lines. That's hard. But what I did not talk about was the sign of work. Is the work going to be positive for a cycle, or is the work going to be negative for a cycle? And to figure that out, let's just imagine calculating work for all the individual pieces. So we have 3 processes. So here's one of them, right? And the work done would be this, right? This is the area under that line. And so the work done would be that much. And then let's say that I, pick some sort of different color. And I look at the area under this line. Actually, I don't want to use red for reasons that will become clear here in a moment. Right. So let's say that I was interested in the area under this shape. The work done would just be the area under this line, right? So what about for this one? Well, what we're going to notice for this process right here is that all of the area under this process includes all the area under the other processes as well. All the area under the other processes as well, right? So all the work that this first process B to C does, and the process that C to A does, is also done in process A to B. But what are the signs of the work? Well, for these two, the signs are positive, right? So this process involves a decrease in volume, so that's a positive change in work. This process is also a decrease in volume, so that's a positive change in work. But this process has a negative change in work because it's an increase in volume. But this process includes everything that the other processes does. So we have one really big process that's negative and 2 smaller processes that are positive. And so the total amount of work is going to be negative. And there's actually a nice little rule that we can follow if you want for cycles. And the rule is this. Is that if your cycle is going clockwise, this one's clockwise, right? It's going around this way. If your cycle is clockwise, then work will be negative. And if it's counterclockwise, then work will be positive. Okay, so that's how we would deal with cycles. Right? But the reason, again, is that one of the processes is doing all the work that the other processes are doing and more, except it has the opposite sign.
Apple Music doesn't support any artists.
My HomePod is talking to me. Apologies. Okay, so work is negative. What about heat? Well, again, you might be tempted to go to an equation, and this time we actually do need an equation, but we don't actually have to do any calculations with this. We need this one. Del U is equal to Q plus W. And let's look at what we know so far. We already know what U is. We already found it in the previous part, or at least delta U, it's 0. And we also know that that work is negative, right? So we have 0 is equal to Q plus a negative number. And so Q must be a positive number. In other words, if the change in the internal energy is 0 while the work is positive, then, or excuse me, while the work is negative, then heat must be positive. Is positive, right? And so one thing that we often call these things heat engines, right? So what does negative work mean? Negative work means that the gas is giving energy to the surroundings, right? The gas is taking some of the energy that the gas has is being sent out into the environment. And if you're clever, and human beings tend to be very clever, if you're clever, you can capture that work and do something interesting with it. This is how a car engine works, right? A car engine works by letting a gas expand and then taking that energy that the gas is giving away as it expands and using it to drive the car forward, right? But what do you have to do? You have to give it heat in order for it to do that. You have to give it fuel, if you want to think about it that way. So that's what we call a heat engine. And so there's a lot of different types of heat engines. We're not going to study them, but the different ones are useful for different context. Okay. 3, determine the volume at state A, show your work. Recall, process A to B is a constant temperature process. Okay, so this problem has given me a hint, and so I'm going to use information from the hint to build my solution. So the first thing I might say is, well, it's telling me that process A to B is a constant temperature process. So let's capture let's see what information I can get about that process. Well, one piece of information that I can get about the process is the pressure at both of these spots. So at point A, we can get pressure. It's this. And at point B, we can get pressure. So I'm going to write those down. Because they might be useful. So pressure is equal to 12 times 10 to the 5. And at state B, pressure is equal to 6 times 10 to the 5. And I also have the volume at state B, right? I found it on the diagram. It's right here. So I can write that down. Volume is equal to 2. Sorry, I already lost it. Did I write something? Oh yeah, this was not 6. My mistake. This is not 6. This is 1. And at state B, it is 12. Did I write everything down right? No, I made all sorts of mistakes here. Wow. This is 6 times 10 to the 5. This is 1 times 10 to the 5. This is 12 times 10 to the negative 3. I read those off of the plot, but apparently not very well. I guess we'll blame Kofic brain for that one. But these are finally the right numbers, right? These are the numbers that's on the pressure volume diagram. So what are we going to do with this information? Right? It doesn't seem that we've actually gained anything from this because I'm being asked to calculate the pressure or the volume at state A. Well, the important thing is this. Recall, process A to B is a constant temperature process. So is there anything that we know about that relates pressure and volume to temperature? The answer is yes, of course there is. We have the ideal gas law. We have the ideal gas law. And so what we know is that temperature is going to be the same for both of them, but we can actually go a bit farther than that. So temperature will be the same, right? Because as we go from process A to B, because it's a constant temperature process, so the temperature at state A will be exactly the same as the temperature at state B, right? So that's perhaps useful. But what else will be the same? It turns out that the number of moles will also be the same. Now, this is not something that's been stated explicitly, but it's something that is generally going to be true about our system, right? It's generally going to be true about our systems. We are not in this class going to deal with systems where the number of moles is changing in the middle of a problem. That is, the math just gets weird and tricky. And so we're not going to do that. We're always going to deal with processes where the number of moles is constant. So the temperature is constant. The ideal gas constant is a constant by definition, and the number of moles is a constant, which means this entire number must be the same for the entire process, which also means that this entire number must be the same for the entire process. And so what that tells us is that if we, no matter where on this process we are, anywhere between A and B, the pressure times the volume will always be equal to the same number. Now, we don't necessarily know what that number is, but we know it will always be the same. And so what that allows us to do is say, okay, well, if this is true, if this number, if this is true, we can write it like this, right? Oops. The pressure times the volume will always be the same at every point along an isothermal process, right? Again, it comes from the ideal gas law. The temperature is constant, the number of moles is constant, R is a constant, and so the pressure times the volume for an isothermal process will always be the same. This equation, if you take chemistry, excuse me, if you take a chemistry class, it has its own name. I don't remember what the name is. It's been a while since I took that class, but it has its own name. But the important thing to remember, it's only true for constant temperature processes. So notice we have, if with this equation, we actually have 4 of these. We have the pressure at state A, we have the pressure at state B, and we have the volume at state B. And so we can just, I should write this as A and B, A, and B. And now we can just plug in numbers. So we have the pressure at state A, which is 6 times 10 to the 5 pascals, times the volume at A, which we're trying to find, is equal to the pressure at B, which is which is 1 times 10 to the 5. And the volume at B, I want to include the unit here, and the volume at B, which is 12 times 10 to the negative 3. And if you plug all these numbers in, what you would get out is that the volume at A is equal to 2 times 10 to the negative 3. So the actual calculation itself is fairly straightforward, but we just had to use what we knew about the process, the fact that the temperature was constant, to figure out that we could do this. Okay. Lastly, it says determine the work done in the process B to C, show your work. So let's go to the pressure volume diagram and look. And the nice thing about the process B to C is that it's a constant pressure process, right? This is a constant pressure process. And so we can use the simple equation that we have for calculating work. Negative pressure times the change in volume. Just like that. And so what I would do is I'd first go up here and find the pressure. So this is equal to negative pressure, which is 1 times 10 to the 5, times the change in volume, which is the final volume minus the initial volume. The final volume is 5 times 10 to the negative 5, or excuse me, 10 to the negative 3, minus the initial volume, which is 12 times 10 to the negative 3. And when you plug all this in, we get work equals 700 joules. And there we go. There's our answer. So this is the case for a lot of these thermodynamics problems, is that a lot of the individual calculations are not that hard. But what the hard part is figuring out which order you need to do the calculations in to get to the final answer. And that requires us to sort of have a sense of how all of the different things that we know about a gas relate to other things in thermodynamics. So for example, the temperature of the gas has to do with its thermal energy. That makes sense. But it also is related to its pressure and volume by the ideal gas law. And so we sort of have to, a lot of our work is just figuring out which stuff we need to calculate before we actually go through and try to calculate it. But each of the individual calculations themselves are usually quite straightforward. There are some that get really hard, but that's why we've gotten rid of, say, the, we're not asking you to do the integral, right? For the, even though work is technically an integral, we're not asking you to do the integral. We're not learning a ton about the details of like adiabatic processes, right? At least not the math. Again, because the math just gets weird. Okay, so that's that problem. Like I said, this is one of the practice problems that has been posted. So you're welcome to go and look at it again or look at a different one. But yeah, that's all I have to say about that. Okay, so any questions or comments before I move on to talking about a little bit of new content? Okay. All right. All right. Okay, so let's talk about this next thing. So if you're following along, oh, I can literally fix that right now. I probably just forgot to publish it. Okay, yeah, you should be good to go now. It's fixed. There's always just one more button that I have to press that I forget to press, but it should be fixed now. Okay. So for problem, okay, so for this next thing, I'm gonna, if you're following along in the slides that I posted, there are a couple slides in here about enthalpy. I'm going to skip those. You're going to see it in DL. Why am I going to skip it? Because we're just not going to talk. I'm just not going to test you on it. It's an interesting topic, but I don't think a particularly important one for this particular class. So I'm not going to test you on it on a quiz or exam. You will see it in DL for a minute or two, but other than that, you don't need to be too worried about it. So I'm just going to skip over those slides for now. And we're going to talk about this instead. And this is where the flipping coins is going to come into play, although it's not necessarily going to be totally obvious why until we spend a little bit of time with it. So we're moving into this thing called statistical mechanics. Now, statistical mechanics is actually one of my favorite things in physics. I think it's super cool and interesting. We are not going to get the time to study it in as much detail as I might like, but that's okay. And part of the reason that we won't get to do it is that we don't expect you to know how to do statistics in this class. So the word statistical is in the name, statistical mechanics. We're not going to actually do any real statistics. There are some statistics that we've sort of hidden in a couple of the topics, but we've never actually asked you to do statistics, and we're not going to ask you to do it now. We're just going to use some interesting facts to learn a little bit more about the way gases work. So, and to do that, let's do this thought experiment. Let's imagine we were trying to build a perfect model of a box of gas. And what I mean by a perfect model is it's a model where we could answer any question we could ever want to ask about the gas. No question would be too pedantic or too high level or anything like that, right? It's a perfect model. It can answer any questions. How might we have to do that? Well, the way that we would have to do that is that we would have to describe each individual gas particle. So there it goes. We would have to describe each individual gas particle, right? We'd have to know exactly where every particle in the gas is and where it's going at any moment in time, because if it's a perfect model and it can really answer any question that I might want to know about the gas, that would include questions like, where is this particle and how fast is it moving? And we could perhaps imagine doing this for a very small number of particles, like the number of particles in this box, but it is impossible to do for the numbers of particles that we sort of run into in our everyday life. So usually we're dealing with systems that have like modes or moles of particles, right? Like just huge numbers of particles. And so building this kind of model is just not possible for these large numbers of particles. It's just not possible. And so what do we do with that? Well, instead of thinking about each individual particle, we instead think about the statistics of all the particles as a whole, Now, I said we aren't going to actually do statistics, and that's true. But we're going to think about it a little bit. We're going to think about some very basic concepts of statistics and how they might apply to particles. And we need to introduce these two big ideas for what we're going to talk about. And there's this idea called a macrostate and a microstate. What is the relationship between these two? What are they? What is the relationship? Well, a microstate, and we're going to do an example here in a minute that's not going to involve particles. It's going to be a little bit more straightforward. That'll hopefully help illustrate this. So if this doesn't make total sense when you first read it, when I first say it, don't worry about that. But a microstate is the description of each individual particle in all of its annoying detail. So that is, we take all the particles, we look at what all of them are doing, we label them, we figure out how fast they're moving, what direction they're moving, are they rotating, are they vibrating, all that stuff. And that was what we would call the microstate. Whereas the macrostate would be, okay, we zoom out, we look at the whole box and we say, well, what's the pressure of the gas in this box? What's the volume of the gas in this box? Those kinds of things. But how are they connected? Well, there's two ways that they're connected. And one way we'll talk about in a minute, but the other way we can talk about now, which is that the thing to keep in mind is that each microstate has a macrostate. What do I mean by that? I mean, if I gave you the microstate, if I told you the exact position and direction and all of that stuff of every particle in your substance, you could tell, well, could you actually calculate this? Perhaps, perhaps not. But it would be possible in principle to then figure out everything else about the gas. You could figure out the pressure, you could figure out the volume, you could figure out the temperature, those kinds of things. So that's one of the connections. But in order to see the other connection, let's take a moment to think a little bit more deeply about what I mean by macrostate and microstate. And to do that, let's think about a much simpler case. Let's think about a coin, right? So this is a nickel, right? It has a head side, which has a little head on it, and a tail side. Oh, I don't know if you can actually see that. Not that it matters. Hopefully you've all seen a coin at some point. It's got a head side and it's got a tail side, right? And I can imagine flipping the coin. And the thing we know is that if we have a fair coin, right? A fair coin, about 50% of the time, it's going to end up on heads, and about 50% of the time, it's going to end up on tails. So let's imagine that we flipped this coin a bunch of times and wrote down exactly the what we got. So I flipped the first time, it's tails, so I write down tails. I flipped the second time, it's heads, so I write down heads. I flip the third time, it's tails, I write down tails. I flip the fourth time, it's tails, I write down tails again, and so on, right? And so on. And at the end, what do I have? I have a list of heads and tails in the order that I got them. The microstate in this case would just be the specific order of the heads and tails, right? So it would be like heads, tails, 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 heads, 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 tails, tails, heads, tails, something like that. Whereas the macrostate would be the total number of heads and tails. So I might say there were 4 heads and 5 tails. That doesn't tell you anything about the exact order that the heads and tails came up with. That is just the total numbers of heads and tails. So that's a simpler example where we can sort of see the difference between the microstate and the macrostate. The microstate gives us the exact details about every individual piece of our system, whereas the macrostate just answers some higher level question. Now, of course, if I gave you the list and I said, this is the exact order of heads and tails I have, this is the microstate that I got, you could take that and you could count up the heads and give me the macrostate. You could say, oh, I counted it up and you flipped 6 heads. So the macrostate is you have 6 heads, right? But you can't go the other way, right? I can't say, I got 6 heads and 4 tails. Now you tell me the exact order of heads and tails I got. That's not possible. Okay, so what does this have to do with gases? Well, to answer that question, we need to know this. And this is the secret. The secret is that every microstate in a system is just as likely as every other microstate. So what does that mean? It means that if you flip the coin, let's say you flip this coin 6 times and you got 6 heads in a row, that is every bit as likely as getting heads, tails, heads, tails, heads, tails. Now you would say, wait a minute. But in one of them, I'm getting 6 heads in a row. And in the other one, I'm getting half heads and half tails. So surely the one with half heads and half tails is more likely, right? It turns out that it's not. It turns out that it's not. The difference is not that the one microstate is more likely than the other. The difference is that one macrostate is more likely than the other. It is more likely that you will flip half heads and half tails than that you will flip 6 heads total. Why is that? Well, the reason is that because there are other ways to get half heads and half tails. So the one that I have on the screen is just one of them. I could imagine some others. So I could, for example, say, well, oops, gosh darn it. Okay, that's back. So for example, I could say, well, let's imagine that I flipped heads, 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 tails, tails, tails. Oops, tails, tails, tails. Right? This is another way that I can flip a coin 6 times and get 3 heads and 3 tails. There are no other ways to flip a coin 6 times and get 6 heads, right? There's only the one. There are only the one. And so even though each particular way of flipping the coins, the exact order of heads and tails that you get is equally likely, the case where you have half heads and half tails is more likely than the case where you have 6 heads, because there are more ways of getting half heads and half tails. There are more different possible microstates that you can get that have half heads and half tails. This just says that. And so it turns out that you can calculate the probability of a macrostate by calculating the number of microstates that give you that macrostate and dividing by the total number of microstates. So for example, for 3 heads and 3 tails, for half heads and half tails, there are 20 total microstates. Right? So there are 20 microstates that give you half heads and half tails, and 64 possible different outcomes that you can get when you flip 6 coins. So if you flip a coin 6 times, there are 64 different possible outcomes that you have, and 20 of those will give you half heads and half tails. Well, only one of them will give you 6 heads. And so as a result, the probability of getting half heads and half tails is 20 over 64. Half heads, heads, and half tails, right? There are 20 different ways you can get half heads and half tails. So you could get heads, 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 tails, 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 or you could get tails, 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 heads, 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 or heads, tails, heads, tails, heads, tails, or tails, heads, tails, heads, tails, heads. There's all these different ways that you can do it. But there's only one way you can get 6 in a row. And so the case where you get half and half is more likely. But what does this have to do with gases? Well, let's imagine a system where we have a box and and it has nothing in it right now, and we're gonna put a divider right down the center. It's a fake divider, it's not really there, but we're gonna imagine breaking this box into 2 pieces. And let's imagine that we're gonna put particles of gas into the box 1 molecule at a time, 1 particle at a time. And when we do that, we're going to flip a coin. And if the coin is heads, we're going to put the particle on the left-hand side. And when the coin is tails, we're going to put the particle on the right-hand side, right? Over time, if we did this, about half the particles would end up in the left and about half the particles would end up in the right. Now you could imagine doing this again with a box with 4 spots, right? You could roll a 4-sided die. If it was a 1, we would, put it in this corner up here. If it was a 2, we'd put it in this corner up here. If it was a 3, you'd put it in this corner and 4 on, and so on. You can imagine continuing to do this, breaking this up. But of course, when we put gas into a box, this is not how it works. We're not adding individual particles. We're just putting a ton of particles into the box together. So why is this relevant? Well, let's imagine we have this box of gas here, and we shove all the particles up into a corner. We shove all the particles up into the corner, and then we let them go. So we're taking all these particles, we're pushing them up here. And then, so they're all scrunched up in here, and then we're going to let them go and spread out. Well, what's going to happen is the particles are going to kind of bounce off each other in random ways, and then they're just going to fly in random directions. And the way you can think about flying in random directions is the particle is going to kind of roll the dice and then just go a direction based on what the dice says. Right? It's going to roll a dice and go a direction based on what the dice says. And so what's going to happen is that you're going to have some particles going this way, some particles going that way, some particles going to go going another way. And the result is the particles are going to sort of spread out throughout the box evenly. Right? This is where the statistics comes in. We cannot say anything about what any one individual particle is going to do. I cannot pick one particle at random and tell you immediately which direction that particle is going to go. But I can say that all the particles together, if you add if I just consider them all as a whole, I can say that because of the way that probabilities work, that the particles are going to be spread somewhat evenly throughout the box. Right? What's another way of saying this? Another way of saying this is that there are more microstates where the particles are spread evenly throughout the box than there are microstates where the gas particles are up in one corner, all by them, all shoved up into one corner. Now, is it impossible for, if the particles are just bouncing around randomly now, is it impossible for the particles to then randomly end up back in one corner of the box? No, it's not. But it's sort of like flipping a coin 100 times and getting heads every single time. Is it technically impossible? No. Is it likely at all? Also no, right? It's basically impossible. It's never going to happen to you, right? If it did happen to you, either your coin is not fair, right? It's a weighted coin or something, or there's some real weirdness going on. And so we can think of the gas being spread out randomly as like getting about half heads and half tails. And we can think of the gas being up in the corner is like getting all heads and no tails. Right? But the special thing is that if we do sort of push the gas into a corner and then let it go, it's going to start basically rolling dice, flipping coins, and spreading out again. So the way you can imagine this is like, imagine that I had 100 coins and I placed them all on heads. Right? I just put them all heads up on my table, and then I went through and I flipped each one individually. Now we would not have all heads anymore. We'd be back to about 50% heads and 50% tails. It's sort of like that. We shove the gas up into a corner. We're putting all the coins on our table on heads. We let the gas go. The gas particles are rolling dice, and you can think of that as going through and flipping all the coins, and they're sort of spreading out randomly because of that. Okay, so how does this relate to thermodynamics? So how can we relate this to thermodynamics? How can we relate this to things like pressures and volumes? We're going to explore that a little bit next week. But the big idea is going to be this. We're going to talk about this more next week. Usually, second law of thermodynamics is introduced with this thing, excuse me, this thing called entropy. We're not going to talk about entropy today. I'm going to talk about it next week. But the way we can think about this is that a closed system, so this is a system where no energy is going in or out, nothing is affecting the system, it's just doing its own thing, sitting there. A closed system will always eventually reach the macrostate that is most probable. A closed system will always eventually reach the macrostate that is most probable. So again, for example, go back to the gas case. We shove all the particles up into a corner and then let them go and let the system just do its thing. Those particles are going to spread out. Why? Because the macrostate, or the state, if you want to think about it that way, where the particles are sort of evenly spread out throughout the system, is much more probable than the state where all the particles are shoved up into a corner. Now, why is that? Because there are just more microstates that involve particles sort of evenly spread out than there are yes, then there are microstates where the particles are all in one corner. And so the macrostate where the particles are spread out ends up being more likely. And the cool thing about this is that it turns out that some of the quote unquote laws of physics are actually just the second law of thermodynamics in disguise. So for example, why does heat move from a warm object to a cool object? Why does heat move from a warm object to a cool object? Well, in our class, we sort of just accepted that this is the thing that happens, right? I have a hot thing and I have a cold thing, and I put them together. The hot thing cools down, the warm thing or the cold thing warms up until they reach the same temperature, right? That's what we sort of said. But why does this happen? And the reason turns out to be that when that happens, the number of microstates that is available to the system actually increases. We have not yet learned how to calculate that. We're going to learn a little bit about how to calculate that next week. But it just turns out that this happens. And so the system naturally, because of the second law of thermodynamics, will head in that direction. It'll say, hey, I'm in this state right now. If I were to go to this state, I would have more microstates available. And so I'm going to head towards that state or macrostate. So, okay, so why am I saying state and macrostate interchangeably? Well, one of the reasons is that in an older version of this curriculum, the macrostate was sometimes, we just called it a state. If you go out and search for thermodynamics on the internet and you search up macrostates or microstates, people are usually going to talk about microstates and macrostates. They usually won't talk about microstates and states. So that's why we changed it to microstates and macrostates so that you can go look it up, right? If you go online, you look up macrostates, you're going to get information that makes sense, hopefully. However, it's also because the thing that we think of as the macro state of the system is also the thing that we previously have thought of as the state of the system. So what is the macro state of a box of gas involve? Well, it involves things like the pressure, volume, and temperature of the gas, or what we have previously called the state of the gas. So they're sort of the same thing, right? The microstate is something different, but the macrostate and the state is basically the same thing. And so again, for any system, a transfer of energy in the form of heat, right, from a hot object to a cold object, one way to think about why that happens is that the second law of thermodynamics says that the closed system will always eventually reach that macro state, right? It's going to always do that because that increases the number of microstates that are available to it, or it's moving towards a macro state that is more probable. That's another way of thinking about it. There are a lot of systems that behave like this. Certain chemical reactions are this way, right? When the chemical reaction happens, the number of microstates available to the system is going up. There are a lot of different systems that behave this way, right? So a lot of the laws of physics are secretly the second law of thermodynamics in disguise. All right, so that is the material that I had. I have office hours today. Those will, of course, also be online. My quarantine, the latest my quarantine can end is afternoon Sunday. And so I will definitely be ready to teach again by Monday. I'm, following university guidelines, which means if I test positive, basically my fifth day is the end of the day, Tuesday. And so if I test negative, on like Thursday or Friday, then I'm good to go, at least to leave quarantine. But even again, if that doesn't happen, I should be all good to go by the end of the day, Sunday, which means Monday we should be all set. So that's all. I will just call it there. Give you all 20 minutes of time back. I will go ahead and upload those videos, the short videos for all of these topics later today. But of course, I will be posting this recording very shortly. If you have questions, please feel free to talk about them right here. Post them in chat or raise a hand. Or also you can, of course, come to my office hour later today. I'm sorry that my brain is a little bit out of sorts right now. So I blame the sickness, but I should be better in a couple of days.